first and the second left-hand rule are telling us the relationship between the induced magnetic field that the charge moving is creating, and the third is telling us what is happening with the charge that is moving is placed into a external magnetic field. What is the force that the charge is experiencing, the charge that is moving is experiencing as a result of the external magnetic field. So now if on the first left-hand rule we had the charge moving into a straight line, and then fingers were used to define the direction of the magnetic field that the charge was inducing. And on the second one was that the charge was moving into a coil, and the thumb was telling us what is the direction of the magnetic field that the charge moving was creating, was inducing. The third left-hand rule, well, your left hand will be open. So the fingers will tell you the direction of the external magnetic field that the charge is placed at. The thumb will tell you the direction of the electron. And if you know the direction of the either conventional current or the positive charge, you will switch it. And the palm will be the start of the magnetic force that the charge moving is experiencing. Now, those three directions are perpendicular to each other. So if you open your left hand rule and then you tie your fingers and open your thumb, then you will see that the fingers and the thumb will create a 90-degree angle or close to 90-degree angle, and a force or a vector that it's starting at your palm and is going away from your palm will be as well creating a 90-degree angle. So on this case, the magnetic force that the charge is experiencing is mutually perpendicular to the velocity or the direction that the charge is moving, as well as the external magnetic field that the charge is placed to. So this is how we will use the third rule. Now, let's suppose that we have those examples here. So we have a charge that is an electron moving on this direction, and then an external magnetic field that is into the page. Now, let's see what is the force that the electron is experiencing. So now, we have a negative charge, so the thumb will be up, will not change the direction. The fingers will be to the field. So put your fingers to the field. Therefore, your palm will be facing east. So magnetic force will be on this direction. Okay, let's see another example. Let's suppose that we have now an electron that is moving in the east direction. And then we have a field, that external field, that is into the page. So your thumb will be going east, your fingers will be into the page, therefore the palm will be faced south. So magnetic force will be going down south. Okay, now the question will be, what if the velocity and one of them magnetic field direction of the external magnetic field are parallel to each other. So what will happen in the case when the electron and the magnetic field are in the same direction? Then magnetic force is equal to 0. There is no magnetic force that they will experience. Okay, so the magnetic force, velocity, and the magnetic field, the external magnetic field, are all mutually perpendicular to each other. Okay, the formula that calculates it, the formula that calculates magnetic force is QVB. So it's a charge moving into a magnetic field, external magnetic field. You will not see any case in which those forces, those quantities BVQ are BVFM are not mutually perpendicular to each other. So they always will be perpendicular to each other. And this is why in your formula sheet you have something like perpendicular or sine theta, something like that. Okay, so let's suppose that I will bring a picture here so that we can deal with. Let's suppose that we have a situation like this. North of magnet is here and south is here, and we have a current that is like a conducting current that is here. Let's suppose that what we have here is the motion of the positive charge, or you can say alpha particle, you can say intensity of the current, or conventional current, or whatever you want to say in terms of it. So what we are doing here is a positive charge. So now the magnets, so those two magnets, are creating a magnetic field, an external magnetic field, not the field that the charge is inducing as it is moving into a wire. Okay, not that. So the direction of the field that is created on that case is going from north to south. Okay, so this is B. Now, alpha particle, or intensity of the current, so or the positive charge, is going into the page. So your thumb is going into the page. However, since it is a positive charge, and we are talking left hand here, since it is positive charge, then we switch it. So we make it out of the page. Your fingers are telling you that magnetic field is to east. Therefore, the palm is headed down the page. Okay, so its palm is headed down the page. So that means that magnetic force is on this direction. And so we always are using, again, I want to emphasize it, that we always are using the left-hand rule, because majority of the students are right-handed, so that we will just keep this. However, you are free to use the right hand for positive, left hand for negative, or just a right hand or just left hand. You have to keep in mind that when you are using just left hand, then you have to switch the direction for the positive charge. And if you are using right hand, you have to switch the direction for the negative charge. Okay, so as I said, magnetic force is always mutually perpendicular. So magnetic force is mutually perpendicular to the velocity and perpendicular to the magnetic field out of strength B. Now, the formula that calculates the magnitude Again, we are dealing here with direction is defined in one way and magnitude is defined on the other way. The formula that calculates the magnitude of the magnetic force is QVB, where Q is the charge in coulombs, okay, moving charge in coulombs. V is the magnitude of the speed or magnitude of the velocity that the charge is moving, and it is in meters per second. B is the magnetic strength, magnetic field strength, and it is measured in Tesla to honor the work that Tesla have done. Now, on some cases, you will see this formula as QVB sine theta, where theta is the angle between the velocity and V. However, since I said in the cases of the physics 30, angle theta is 90 degrees because they are mutual perpendicular to each other. So that results into sine theta as equal to 1. So what we will do is we will just use QVB for physics 30 and keep in mind that they are on the case when they are mutually perpendicular to each other. Okay, let's bring an example here that will make us calculate the force and probably acceleration. So let's suppose that we have a particle that has a mass of, let's say, 15 milligrams, and it has a charge. The charge of the particle is positively 1, and it is 3.2 mu coulombs, and it is entering into a magnetic field that is with an intensity of 0.025 Tesla. What is the force? And the magnetic field is something like this. So let's say that here is north and here is south. So we have a charge that is entering here with a velocity of, let's say, 50 meters per second. What is the magnetic force that the charge is experiencing, and what is the acceleration as a result of this force only, not the gravity? Okay, so first of all, let's define the direction. So in this case, what we have is the object is having is placed, the charged object is moving, and it is experiencing an external magnetic field. So magnetic field is leaving north going to south. So this will be B, and this will be V. Okay. The direction of V. So now we have a positive charge that is going east. If we are using left hand, then we will switch the direction. So we'll make it the thumb going west, and magnetic field is going down. Okay, it's going down because if the north is up and south is down, and then the palm will be into the page. So magnetic force will be into the page direction. Now let's figure out the magnitude. So magnetic force will be QVB, and the charge is 3.2 times 10 to the power of -6 coulombs, times the speed is 50, I believe, meters per second, times 0.025 Tesla. So magnitude of the magnetic force using your calculator will be, let me use my calculator, 4.0 times 10 to the power of negative 6 newtons. And if we are looking for the, and this is into the page, we are looking to define the magnetic force as a vector, then we will say magnetic force is 4.0 times 10 to the power of negative 6 newtons into the page. And now if we are looking for the acceleration as a result of the magnetic force, based on the second law of Newton, we can say that acceleration is force over mass. So this will be 4.0 times 10 to the power of negative 6 newtons over mass was, I believe, 15 milligrams. So it will be 15 times 10 to the power of negative 6. So then the acceleration using your calculator, divide by 15 times 10 to the power of negative 6 equals to 0.27 meters per second squared, and will be into the page as well, because the acceleration and force will have the same direction. Okay, let's take a look at another example where we are calculating and figuring out the direction of the magnetic field strength of the outside one. If the, so what is B? If the electron is, so electron is experiencing, or no, it is moving with a velocity of 420 meters per second, and it is deflected by a force of 2.30 times 10 to the power of a negative 19 newtons. Now, from the formula, what we have is that magnetic force is equal to QVB. Even though that Q is not quite given, we know that it is dealing with an electron, so we do know what Q is, we do know what V is, 420, and we do know what the magnetic force that the electron is experiencing, so we will find B. So B will be magnetic force over Q times V, or in our case will be 2.30 times 10 to the power of negative 19 over 1.60 times 10 to the power of negative 19, because electron has one elementary charge, times 420. So in your calculator, 1.6 times 420 will be magnetic field strength will be 3.42 times 10 to the power of negative 3 Tesla. And if they are asking you to record your answer into A dot B C times 10 to the power of negative D and record only the digits, then you should record only 3423. I hope that this makes sense. Let's see now, when we have an alpha particle, that is entering into a field, magnetic field that is going up with magnitude of 30 millitesla, and the speed of the particle is, let's say, is velocity of alpha particle is going up as well, and it is 500 meters per second. What is the magnetic force that the alpha particle is experiencing? And since they are collinear, the magnetic force is equal to 0. So there is no deflection on this case. Okay, so this is the third left-hander rule lesson, and we will deal more with now a charge moving into a magnetic field and the applications of it in the next videos.